Hello, everyone. Again, welcome. As noted, I'm Jillian Walker. Thank you for taking the time to join us today for our session on intelligent robotics for smart manufacturing. As noted, today I have with me Isaac Premsing and Kalyani Debrukar, who have been researching this space and are happy to give an overview of insights learned from both market and technology perspectives. But I guess the question is why this topic now? Manufacturing, of course, is facing pressures from multiple angles. There are supply chain disruptions, rising input costs, unpredictable demand, and perhaps even most pressing, a massive labor shortage now and continuing on the horizon. We think about even in the US alone, more than 2 million skilled roles could go unfilled by 2030. So these kinds of challenges really mean that relying on traditional, rigid kind of automation that we've seen historically won't be enough moving forward in the future. So today's conversation really is about how intelligent multitasking robots are transforming that shop floor. We're going to explore how robots evolve from executing fixed instructions to becoming adaptive, polyfunctional, really kind of teammates. And we'll keep this conversation accessible. You don't need to be an engineer to get value from this session. Our focus is going to be on the strategic implications for manufacturing leaders, for marketers, and for strategists. So here's how we're going to spend our time today. We're going to start with the market context, the scale of the opportunity, and the kind of mega forces or forces that are reshaping robotics. Then Kalyani will walk us through what makes robots intelligent, breaking down the 5 intelligence layers and sharing examples that really bring them to life. We'll also run a live poll to hear some of your perspectives. And then we will go a little bit deeper into the roadmap for 2040, how these capabilities and intelligence are expected to mature over the next 15 years. And then from there, Isaac will talk a little bit more about the ecosystem and the value chain dynamics, who some of the key players are, and where competitive control points are shifting. He'll also cover some critical actions that stakeholders can take to succeed in this new environment. And then finally, we will wrap up with some Q&A. So do please stay engaged, ask questions in the chat as we go, and we'll tackle them at the end of our session. Okay, so getting into some of the market highlights. So here you can see that we highlight the scale of the opportunity in industrial robotics software. So by 2030, we project the market will reach nearly 34 billion USD, and that's growing at a compound annual rate of almost 24%. So this tells us that the real shift, the real value shift is happening in that software layer, where intelligence, where orchestration and autonomy are being created, and not really in the hardware alone. On the right here, you can see that today's spending footprint, where China is already the kind of dominant market, accounting for more than half of global spend. Japan, the US, Korea, Germany follow, with the rest of the world together making up about 17%. And this distribution reflects both China's massive installed base for robotics, but also its strong policy push toward automation. And this implication here is that while growth is global, leadership will come from those markets that can scale both adoption and innovation. So as per our analysis, the winners won't just be the companies that are, selling more robots. They will be those that are capturing value in that software intelligence layer, where adaptability, where resilience, where integration with digital factories really is truly defined. And that's where I think long-term differentiation and competitive advantage is headed. So let's talk a little bit about some of the mega forces that are aligning with this push towards intelligence in polyfunctional robots. And this slide here summarizes the five forces that we see reshaping the future of manufacturing robotics. The first is the emergence and growth of responsive enterprises. And this is the idea that organizations are having to anticipate and adapt to faster changing market shifts. So, unstable supply chain dynamics, things like evolving user demand. In industry, manufacturers face increasing pressure to adapt quickly, and this means that they require their operations to easily pivot to situations, things like shifting volumes, more local customization, variable workforce availability, as we sort of noted in our introduction. Another influencing force is what we call the intelligence continuum, and this refers to the concept of the kind of seamless integration of human intelligence with AI, IoT, cognitive computing, and this is creating a constantly evolving, if you will, intelligence ecosystem. So this is the force that is going to continue to drive increasing expectations for smarter, more capable robots. Next, we have what we like to call next value networks. And this is a term that is referencing the reshaping of traditional supply chains and economic relationships into a kind of dynamic intelligence and often decentralized form. And this is really where we're moving more into kind of an interconnected web of producers, consumers, intermediaries that is kind of requiring and enabling a more fluid and efficient and transparent exchange of value. So for this kind of web, this kind of network, value network to really work, manufacturing, to bring it back down to manufacturing, uh, manufacturing itself has to be just as kind of connected and flexible. And that means that robots have to be more software defined, more interoperable, and able to really plug into that kind of digital ecosystem. Polyfunctional robots also, of course, they overlap with the concept of an autonomous world, as they could, as they gain more intelligence, operate more independently, enable production lines to reconfigure when needed to advance, and to really kind of push forward that concept of fully lights out operations. And then finally, geopolitics reimagined, one of the other forces that's really kind of overlapping and pushing forward this concept of more intelligent robotics. So many governments are pushing to reshape manufacturing to achieve their own competitive advantage or techno sovereignty or to preserve that capability within their domestic realm. So more intelligent robots offers one way of achieving these goals, especially when we think about high cost economies, again, that may have low labor supplies. So when we look at these forces, what emerges here is a future where intelligence becomes really that defining feature of robotics. And it's enabling these systems to flex with supply chains, to learn alongside humans and in concert with artificial intelligence, and to serve as that backbone of resilient next generation manufacturing operations. So, why is polyfunctionality basically non-negotiable? So here we have some of the drivers around polyfunctionality. So first, again, as we've noted, we do have the anticipation of skilled labor shortages continuing. We've already sort of noted that by 2030, the US could be short over 2 million workers in manufacturing. Things like welding, inspection, assembly, and other skills are roles that are already very hard to fill, and that gap is only going to grow. So, intelligent robots that can cover multiple functions and to pivot across these skills have become one of those ways to bridge that gap. Second, there is a rising demand for flexible automation. So manufacturers no longer want kind of single purpose robots. They need systems that can be quickly reprogrammable and redeployed across these various tasks and various production lines, especially when we start thinking about high mix variable production environments. Third, efficiency and cost pressures. Um, these are intensifying. We have things like inflation, of course, waste reduction, downtime. All of this is a way to kind of control margin. Intelligent robotic systems deliver that ROI through adaptive operations, predictive maintenance, energy efficiency, reducing waste, etc. And then finally, customization and agility needs. So shorter product life cycles, which we are increasingly seeing, and customer demand for greater variety mean that factories have to configure and reconfigure faster than before. So polyfunctional robots make that more possible, enabling multitasking, that rapid changeover that we need for this kind of low volume, high variability production demands. So we believe that over the next decade, the adoption of embedded intelligence will grow faster than the deployment of new robots themselves. Why? Because upgrading that intelligence layer delivers ultimately faster returns, it reduces downtime, and it unlocks flexibility without having to really rip and replace hardware. So the question is shifting now from what robots should we buy to how do we infuse intelligence into what we already have. Over that next decade, embedded intelligence adoption is going to grow. As we've noted, faster than new robot purchases, and manufacturers aren't going to win simply by adding more machines, but by making those existing robots smarter, more adaptable, polyfunctional, because that is really where they're going to find that mode of resilience that is needed to answer some of the demands that we see in manufacturing moving forward. I'm going to pass it over to Kalyani, who's going to talk a little bit more now about the current technology landscape, the roadmap to 2040, and how we see applications of polyfunctional robots evolving.
Thank you, Jillian. So here is a look inside the robotics stack and how it helps explain is why embedded intelligence has become such a critical layer. If you look at the stack from the ground up, it starts with physical base, that is mechatronics and power, drivers and control, along with sensing and safety. Above that, we see motion systems, orchestration, enterprise integration, and security. This is the traditional ladder that robotics has been built on for decades. But the spotlight now is on the middle layer, that is embedded intelligence. This is what is transforming robots from predictable machines into adaptive systems. The fact that it sits right in the center of the stack is symbolic. It connects the raw mechanics at the bottom with the enterprise level systems at the very top. Now let's unpack what happens inside this layer. You can refer to the right side of the slide. The first element we're talking about is human-robot interaction. Robots are no longer just following proximity rules. They are using multimodal cues like vision, engine prediction, force sensing to adjust their behavior in real time. That means interfaces are evolving from rigid safety cages into fluent shared workspaces. The implication is that user interface design in robotics is moving away from static control panels and toward more real time behavior driven collaboration. Next is on device learning. Instead of sending all data back to the cloud for retraining, robots are now using local machine learning pipelines to update their skills on the spot. It's similar to on job training. This shift places the burden on the edge where processors, lightweight models, and real time pipelines have to run reliably on the robots itself. The deeper takeaway is that resilience will increasingly depend on how efficiently intelligence can run under tight compute and latency constraints. Then comes the semantic reasoning. Robots are no longer just reading signals, they're interpreting process relationships using structured models. This is critical because without a shared semantic framework, multi-vendor environments break down. So whoever defines the common ontologies and task graphs effectively defines interoperability standards across the factory. Predictive motion is the next. We have moved beyond simple reactive controllers. Robots are blending sensor fusion with trajectory modeling to anticipate and prevent errors before they even happen. This unlocks both higher uptime and real energy savings. This means that predictive control will become a performance benchmark that OEMs are expected to deliver. And finally, there is autonomous task flow. Robots are now able to orchestrate actions themselves, resequencing steps when disruptions happen without waiting for any human intervention. In practice, this means orchestration logic is moving down the stack. It is no longer confined to the MES or central controller. It is becoming embedded into the robot itself. That represents a major architectural shift where control is becoming distributed and resilience is built from the ground up. When you put all of this together, that is embedded intelligence that becomes a gravitational center of the robotic stack. Hardware will always remain the critical part, but the differentiators of adaptability, resilience, and interoperability are now defined here. The control point in robotics is shifting from electromechanics and PLC code to semantic machine learning pipelines and distributed orchestration logic. Now, let's talk about how the shift is actually happening. This slide captures the shift from how robots work today to what is coming next as embedded intelligence matures. On the left, you can see the now. Robots are still built on static sequential task execution. They rely heavily on kinematic motion control, and most of their behavior is reactive. Much of the intelligence is still dependent on the cloud trained models, and interfaces are siloed, limiting how robots and humans interact. What comes next is context driven autonomy, where robots restructure tasks in real time. Motion control becomes predictive and energy optimized, enabling smoother performance. Reactive logic gives away to semantic reasoning, cloud reliance shifts to adaptive learning at the edge, and siloed interfaces evolve into multimodal collaboration between robots and people. For factories or manufacturing shop floors, the message is very clear. Robots will be able to orchestrate tasks dynamically, which means less manual reprogramming and smoother production. Efficiency will not just be about speed, but also about how you use energy wisely. Decision making will become more context aware, making planning and recovery from faults more reliable, trustworthy. Robots will learn and optimize their skills on the spot, reducing the need for constant updates, and collaboration with people will feel more natural, with multimodal interfaces becoming the standard way of working together. And here is what this means for different stakeholders. So, context driven execution and predictive motion will become table stakes, not differentiators. Product roadmaps have to embed these capabilities into hardware and control system now. The shift to orchestration at the edge means integration strategies must be rethought, which means distributed intelligence will replace central bottlenecks. For intelligence developers, on device learning and semantic reasoning are no longer experimental. They are becoming production realities. Algorithms must be lightweight, explainable, and safe to run on the factory floor. For enterprises operating factories, the takeaway is that adaptability, not scale alone, will define the competitiveness. Investments have to prioritize robots that can reconfigure workflows, cut downtime, and work seamlessly with people. The conviction is very clear. The winners will be the stakeholders who treat context aware autonomy not as an advanced feature, but also the new foundation for robotics. Now, let's hear from all of you. So you should see a poll coming up on your screen. The question is, which of these embedded intelligence capabilities excites you the most? Please rank them in the order of your interest, from 1 being most exciting and 5 the least. The options are autonomous multitasking switching, real-time fault detection and correction, human-robot collaborative safety, predictive maintenance and self-optimization, workflow orchestration across multiple robot types. While we wait for the results, let me share a perspective. Predictive maintenance and orchestration often come out on the top because it has a very clear business impact. They keep the lines running smoothly, reduce downtime, and save cost, directly translating into ROI. But something interesting is happening in the market. The shift is now towards collaborative safety. People realize that no matter how advanced the robot is, worker will not accept it if they do not feel safe around it. Trust is becoming just as important as safety. Let's wait for a couple of minutes to get more responses. Okay.
Okay, brilliant. Yeah.
Yeah. So as we predicted, autonomous multitask switching has gained the most votes, which aligns perfectly with our findings. Okay, great. So let's move on. Okay, now we are talking about intelligence building blocks. This slide looks at these blocks that make polyfunctional robots possible, and more importantly, where control and differentiation will come from. When we talk about intelligence building blocks, we can see how robots are shifting from programmed machine to adaptive systems. It starts with the foundation: interoperability, modularity, and safety. Without these, robots remain siloed and cannot scale across platforms or factories. The next layer is predictive intelligence. Robots are beginning to anticipate deviations, coordinate across fleets, and optimize energy. Performance is increasingly measured by consistency and efficiency, not just speed. Adaptive learning platforms are moving from research into production. On-device learning and few short skill transfer now allow robots to adjust directly on the shop floor. Siemens, for example, has shown how robots can use reinforcement learning directly on controllers to adapt assembly tasks in real time, adjusting insertion strategies based on torque feedback without halting the line. Task flow intelligence is embedding orchestration into robot itself. Robots can now resequence tasks, manage disruptions, and keep production moving. A strong example of this comes from Intrinsic, which worked with DeepMind to demonstrate scalable, adaptive, multi-robot coordination powered by specialized AI models. This shows that orchestrating multiple robots safely and effectively is no longer a future, but the emerging reality. Cognitive and reasoning engines extend this further. Robots can interpret tasks semantically and make context-aware decisions. And the frameworks used here will effectively set future interoperability standards. Taken together, these building blocks do not represent isolated features. They form an integrated intelligence platform where prediction, adaptation, orchestration, reasoning, and collaboration converge. The center of gravity in robotics is moving here. And those who master this layer will define how the next generation of systems compete and scales. Now let's talk about the capabilities of intelligent robots through this capability matrix. On this slide, we are looking at the matrix which shows how intelligence in manufacturing robots is evolving. What we see here is not just incremental improvement in individual features, but the emergence of a backbone that connects task flow, predictive motion, and all the other layers that I mentioned earlier. When these capabilities evolve together, robots move beyond executing instruction and begin operating as an adaptive system. For instance, orchestration and motion control are becoming far more sophisticated. Robots can already coordinate across cells, optimize tasks with impressive precision, and they are starting to anticipate variations and adjusting trajectories before an error occurs. This combination of orchestration and predictive motion means that robots are no longer reacting after the fact. They're managing workloads, balancing lines, and sustaining efficiency in real time, which makes them far more resilient in complex production environments. Reasoning and learning are also moving to the forefront. Robots are beginning to interpret what they see in context so as to detect any defects. It is understood in relation to the process. At the same time, on-device learning allows skills to be adapted locally on the shop floor rather than relying on the cloud retraining cycles. This is an important shift because it means systems can improve while in use, calibrating tools, adjusting to new materials, and even refining workflows without external intervention. And of course, the role of human robot interaction cannot be overstated. Current systems already managed shared zones and predictable handovers, but what is emerging is a much more fluent style of collaboration. We are moving toward robots that understand intent through multiple cues and interact naturally with people in sensitive, high precision environments. Looking across industries which are highly impacted by these robotic systems, including automotive, semiconductors, batteries, aerospace, and electronics, the pattern is very clear. Polyfunctionality is not the result of a single innovation. It is the outcome of connecting the core capabilities I mentioned earlier in a one single coherent system. This is what will allow robotics platform to scale confidently from pilot deployments to enterprise-wide production. Now let's see what the roadmap states. This slide outlines how polyfunctional robotics will evolve over the next decade, moving from foundational to contextual, and finally to cognitive intelligence. The first stage, running through the second half of this decade, is all about laying the groundwork. We see early adoption of semantic task graphs, ultra-fast control loops, and offline reinforcement learning pilots, as I mentioned with an example of Siemens. Robots begin to gain responsiveness and simple autonomy, enough to switch between tasks more seamlessly and support collaborative interactions with people. This stage is about creating the baseline capabilities that allow robots to operate without constant reprogramming. As we move into the early 2030s, robots begin to operate with contextual intelligence. At this point, it is less about isolated functions and more about interoperability across platforms. Adaptive learning methods scale up. Robots adapt skills with very little training data, and reasoning systems become capable of handling probabilistic decision making in complex work environments. In practice, this implies that robots will not only execute tasks, but also make context-aware decisions, which significantly changes how workflows are managed. The final stage, mid-2030s, is when cognitive manufacturing ecosystems start to take shape. Here, we are looking at systems with full autonomy, robots that orchestrate workflows, optimize tasks dynamically, and evolve their policies for end-to-end manufacturing control. Precision improves further with multi-robot coordination and adaptive joint control, while human-robot interaction matures into truly shared autonomy. By this point, the factory floor is supported by predictive, self-optimized ecosystems that can coordinate, adapt, and sustain production lines in real time. The broader point from this roadmap is that polyfunctionality or multitasking is not a single leap. It is a staged journey, starting with building the foundations, then layering contextual awareness, and ultimately reaching cognitive level autonomy. Each stage raises the bar for how responsive, adaptive, and collaborative robots can become, and together they define the trajectory of intelligent manufacturing. So, our conviction at the Everest Group is that the journey from foundational to cognitive intelligence is not optional, it is inevitable. Key stakeholders that embrace these stages will be positioned to lead in agility and resilience. Those who hesitate to take this risk may be left behind as robotics shift from rigid automation to self optimizing intelligent ecosystems. Now, I hand over to Isaac for the further points, that is, ecosystem impact.
Thank you, Kalyani. Thanks everyone for joining. So we've seen the broader context in terms of the macros driving intelligence in robotics, and we looked at the tech stack and how different technology features are getting embedded. Now we will look at how the ecosystem is structured and how it's evolving. So when you look at this slide, the way we wanted to look at it is it's sort of a fan out of different stakeholders who are participating in this ecosystem. And it's clear that embedding intelligence in manufacturing is an ecosystem play, right? So it's not one stakeholder, building systems that have the entire tech stack proprietary, and it's more about interoperability as well. So we are seeing some emergence of new players as well who are redefining traditional playbooks, and they claim strong influence in the type of skills that robots are being designed to perform. So, traditionally robots were programmed to, perform a single repeated task. But in the current scheme of things and looking into the future, we believe that the value creation is shifting from the mechatronics and proprietary controllers and offline programming to software, where the intelligence is going to reside, right? So software solutions are designed to perform semantic perception, task and motion planning, reusable skill sets, and also digital twin validation. So we imagine a scenario where the robot fleet in the shop floor will be interacting with the digital twin of the enterprise, which are going to interact with different factories and the digital twin of different factories across different locations. They'll be optimized based on real-time data and have runtime safety constraints. And this will become more of a foundational characteristic, and that will transform the way manufacturing factories perform. So essentially, all this means that the physical robot can be reskilled by just updating the software. So it's almost like swapping a skill pack instead of retooling the cell, right? So who's driving the transformation and what's really happening in the ecosystem? Right? So at the center of this role transformation, we want to position a company like NVIDIA, who's moved aggressively into the industrial robotics space, and it's essentially disrupting the entire tech stack. So today, the NVIDIA's influence on the robotics ecosystem spans from chips to runtimes to software development kits to simulators, twins, and optimization services as well, along with partner integrations. So the breadth of influence is unusual in industrial automation, and this materially shifts the influence that NVIDIA has across the stack. So starting from the left, we're aware, NVIDIA's presence extends from the silicon or edge compute processors, providing compute starting from their Jetson and IGX families to system software and acceleration solutions that include CUDA, TensorRT, CUDA deep neural networks, and SDKs that are optimized for different pipelines. And these are all essentially to accelerate the time from prototype to production, right? So, and then they have the simulation platform i6sim built on Omniverse, which is now enabled teams from different organizations to generate synthetic data And synthetic data is going to be essential for being able to train and program robots for performing different tasks, essentially in conditions where real-time operating data may not be available, and the history is, locked in certain platforms, so which are not accessible. So for that purpose, NVIDIA has got their synthetic data, generation models, and that's essentially to enable the training and the programming and the validation of the softwares to be accelerated. So testing software in the loop and training policies then can be transferred directly to the shop floor. So the classic example is the BMW's flagship virtual factory, which I think in recent months have been quite well discussed. It's an example of the full factory digital twins using Omniverse to plan robotics and logistics before the manufacturing startup. And are we seeing the screen? Is the slide okay? Yeah. Okay, it's starting. Okay. So yeah, in essence, what we see is NVIDIA is pushing foundational models for manipulation of humanoids as well, and all with the aim to standardize reusable skills, right? So whatever we call them, like agents or task force, which are digital task force performing different tasks, they're all designed to be adapted with minimum data. So, and beyond NVIDIA, we're also seeing the fast followers like Google DeepMind, which is launching their range of Gemini robotics, vision language action models, and the embedded reasoning models that are capable of transferring different productized APIs across different hardware systems. So the scope of play for NVIDIA and Gemini are strategically different. But NVIDIA is positioning as the de facto platform on which manufacturers will design, test, deploy, and optimize robots using their full stack infrastructure. While on the other hand, Google is focused on building the foundational model brains with generalist policies that allow motion and skill transfer with embodied reasoning to perform multi-step sequences. So this is all, the new developments that we see on the intelligence side. And the pure play AI engine providers are also the system software providers in the full stack robotic intelligence platforms that seem to like to push the robot OEMs and system integrators to the left of the corner. If developers build and validate skills in the Omniverse with CUDA accelerator libraries, they'll expect the mechatronics and sensors to work with that particular tool chain. So this essentially erodes the proprietary programming environment that OEMs that have had for many years. But that mode still remains for OEMs that are developing safety certified mechatronics and process expertise. These are areas that they'll still maintain their mode. And OEMs will increasingly choose a pragmatic path by integrating with the robot operating systems to using DDS2, which is essentially the data distribution service, which is sort of enabling the underlying network for interaction into the OPC UA ecosystem as well. So essentially, this is the interoperability layer, which is critical. And this allows the robot operating systems based collaboration across different devices to facilitate seamless data exchange across platforms like the Omniverse pipelines as well. So on the for the system integrators who've always been a critical player in this ecosystem, as productization of route optimization and perception models intensifies, the margins on bespoke code will shrink. That's what we believe in. And manufacturers will also expect them to, align themselves with some sort of a reference stack. Look at, Jetson, ISAC, Omniverse, and then some sort of a glue that comes from the systems integrator. So this means that the power shifts from single components to orchestrated stacks with OEMs and system integrators leaning towards open interoperability, runtime assurance, and outcome contracts. So all based on some sort of a reference stack. while they still keep control of the skills and safety, right? Just to summarize, building the next gen intelligent robots is definitely an ecosystem play where the value shifts from the hardware to the software skill packs and the orchestration layer. NVIDIA's full stack platform is becoming sort of a default design to deployment rail, while Google pushes generalist model brains. And OEMs and system integrators are not essentially sidelined, but they must lean into some sort of an open interoperability and outcome-based reference stacks to keep the control on safety and skills as well. So to the next slide. Yeah. So at the end of this briefing, we would like to offer a complimentary, access to a meeting with our analysts. So I'd like to invite the registrants who are on this webinar to make use of this complimentary session to discuss with any of our analysts on what skills on your frontline can be fast swapped today if you're an enterprise running manufacturing factories. So in this session, we'll probably take you through our lens of how we arrive at the set of functional capabilities that are ripe for fast swaps in your industry and discuss considerations from a people, process, and technology standpoint. So to request access, you can follow the link in the chat and to book a meeting, and our team will follow up to schedule with you. So next we look at the value chain dynamics. So we like to visualize the industry value chain as sort of a series of steps or stages. As you can see, we position different stakeholders on this value chain and extend their presence across different stages where the value creation activities for each of them are evident. So traditionally, the value chain was hardware-led, right? So you had component suppliers and semiconductor vendors at the base feeding into robot OEMs who build the hardware, and system integrators deployed on the factory floor. So that model for single-purpose automation worked traditionally, but it doesn't scale when we're looking at robots which are more adaptable or adaptive and polyfunctional. So now the real differentiation is moving upstream. So the upstream stages from component and hardware to software, middleware and control is where the differentiation is shifting. And essentially in the intelligence and reasoning is where the brains of the robots are getting created. So component suppliers design and build hardware, sensors, end-of-arm tooling. So companies like OnRobot, Shunk, and Kians and Cognix, they're all introducing capabilities that kind of extend beyond the hardware into middleware and inspection applications as well. While the semiconductor vendors who begin at the silicon and edge processors, they're reaching up to the AI SDKs and reference designs as well. So NVIDIA, AMD, Intel, they're all in this space. NVIDIA is one of the ones that has already expanded its reach beyond hardware into simulation and optimization as well with the Groot and NiceXim. So system software stacks is the next stage where we believe there is a little bit of an anchor to consider that they control and stretch into interoperability and safety. So they kind of bridge across different platforms. Companies like Wind River with their RTOS for embedded systems, QNX for foundational software solutions, Open Robotics, which is now a subsidiary of Alphabet, and OPC UA bridges offered by companies like Aviva or Metricon by Honeywell. They're all featured in this stage. And moving further down, so this is where we see the emergence of new players and pure play AI engines becoming more critical in this entire value chain for embedding intelligence. So the intelligence and reasoning is essentially built here, and companies like Covariant or Intrinsic by Alphabet, Google Gemini Robotics, Real-Time Robotics, all of these companies are coming up with AI engines that will enable companies to build intelligence applications for different robots. Full stack robotic intelligence platforms, they span from design simulation to deployment and optimization. Isaac Omniverse, Ready Robotics, ForgeOS, Siemens Accelerator platforms. There are some sort of a partnership play in this layer, in this stage, where we see some news announcements where we want to build digital replicas of physical systems and help them integrate with different analytics engines as well, which will be performing smart actions for different processes and discrete systems as well. So think of this as a closed loop intelligence pipe where we simulate, generate, train, optimize, package, accelerate, and deploy on edge, and then telemeter back to improve the operations as well. So if you consider NVIDIA in this context, it kind of owns the entire upstream step, updates to the brain of the robot, and they move quickly, and they're able to coherently work along with their customers to build and simulate these applications and deploy it in physical systems as well. So on the right, if we get closer to the systems integration and manufacturing, the systems integrators and robot OEMs are still the anchors, for mechatronics safety, offering different apps, twins, and upgrades. ABB, Fanuc, KUKA, Yaskawa, and the Universal Robots, they're all into deployment and services as well. System integrators like GR Automation, ATS Corp, they're all working to build some SLA-backed outcomes, which will enable them to expand beyond the hardware into orchestration and managed operations as well. And then we have the industrial IoT analytics platforms, security providers as well, who are all critical to this ecosystem. So in this context, who holds the control point, right? So increasingly, it is those in the intelligence and orchestration layers, full stack platforms, AI engines, and software stacks. This is where we believe the control lies. They essentially tie the hardware, data, and applications together and decide how adaptable and scalable these systems really are going to be. So it's evident from this value chain dynamics that for robotics, that we're seeing some sort of a compression around intelligence and a concentration there, which will enable systems to be more smarter, but also the orchestration and integration is essential as well. So hardware will always matter, but sustainable differentiation will come from those who can own the reasoning layer and deliver platforms that scale across different industries for unique use cases. Next slide. So here we wanted to look at where the real value in the polyfunctional robotics value chain is moving, right? So we see that the competitive edge now comes from AI-first orchestration, the ability to integrate compute, sensing, and intelligence into a coordinated platform. So on the left, OEMs still play a role, but integration is no longer just enough to have guarantees on the control of the ecosystem, and system integrators are gaining orchestration power by pulling together multiple technologies into cohesive solutions. And at the same time, IoT platforms are capturing operational data that feeds intelligent decision-making, while full-stack platforms are starting to absorb niche roles that used to belong to specialized providers. So two elements are critical. So one is security scaling, right? So that's central to what we do with machines in factory settings. Without safeguarding intelligence layers, large-scale orchestration simply won't work. And software-hardware fusion is critical, and accelerating the integration, allowing for orchestration to extend seamlessly across systems. Those are all critical elements that we need to look for. And at the core, the differentiation is on how can we deliver AI-first orchestration. So when we have a fleet of smart robotic systems performing different tasks using multiple applications, accessing data from different layers in the stack, whoever controls the orchestration of this fleet decides how robots learn, adapt, and coordinate. And that particular stakeholder has the control on the pace of innovation and the flow of value delivered as well. So we believe that hardware value will slowly be eroded, and the winners will be those who own the orchestration, building platforms that unify intelligence and integrate across vendors and deliver resilience at scale. So what should stakeholders do, and how do we see different stakeholders evolve over time to position themselves in the short, medium, and long term? So in the near term, we believe that robot OEMs should align their orchestration with manufacturing execution systems so that robots plug and play easily into existing factory software. AI engine providers should focus on offline reinforcement learning, essentially because there might not be enough data everywhere we need. Training policies and simulation before bringing them to the shop floor. And full stack platform providers need to build integrated orchestration stacks where motion learning and safety all sit together. And system software providers should standardize real-time control loops. So timing is consistent across different robot brands as well. So in the medium term, 28 to 32, the focus shifts more upstream. OEMs will begin to expand into predictive task planning, and AI providers, we believe, will deliver some sort of improvements in few shot task adaptation, platforms that scale into adaptive orchestration across multiple lines. And software providers will focus on delivering cross-platform abstraction, so you can manage mixed fleets through one API, right? So, and looking ahead to 2033 and beyond, we believe that OEMs will orchestrate multi-line systems that rebalance work automatically, and AI engines will advance towards autonomous policy execution, and platforms will consolidate intelligence layers, and software stacks will enable safe cooperative human-robot interaction. So, I'll just close with, a few action items for stakeholders and, looking at distilling the different control shifts to what the stakeholders actually need to do to scale polyfunctional robotics. It is becoming more evident that isolated pilots or demos are a thing of the past, right? So, to succeed in embedding intelligence, companies need a more production grounded and human centered orchestration platform that learns reliably and can be redeployed quickly across vendors and factories. So here are 6 priority actions that we have. So first is to standardize modular task APIs, right? So think of this as building a library of reusable robot skills. If every new task requires low-level programming, adoption will stall, right? So using semantic APIs and OPC UA compatible standards makes skills portable across robot brands, and that will help cut integration delays. Second is to prioritize the safe on-device learning. So reinforcement learning can help robots adapt to variability, but it must be bound by certain safety constraints. So think of this as the focus should be on use cases, specific use cases where real-time feedback loops will improve performance without putting operators at risk. Third is to enable runtime semantic orchestration. So this means replacing rigid scripts with structured ontologies and execution engines that connect robots directly with MES and digital twins. So this benefit is that when production shifts or reconfigures, the robots cannot adapt dynamically and rather than requiring a manual reset. Fourth is to mature shared autonomy models. So robots and humans will increasingly share work. We need architectures where perception and decision logic allows fluid handoffs and safe overrides. For example, in a co-assembly or inspection task where both parties, humans and machines, interact in real time. And fifth is to expand the low-code ecosystem support. So not every factory has programmers in the front line. It is important to introduce standardized modular visual interfaces that can allow even technical, non-technical factory specialists to configure and monitor robots. So this reduces commissioning time, lowers the support costs, and improves optimization after deployment. And finally, it is important to align tool chains with deployment realities. So too often, solutions are validated in labs, but they fail miserably in production environments. So co-developing tool chains with line engineers ensures semantic integration, learning stability, and the control logic will hold up in real-world conditions as well. So the takeaway is quite simple. So scaling and rolling out intelligence for robotic fleets from pilots to enterprise-wide adoption is essentially an ecosystem play where robots can safely learn and interoperate across different platforms. So it's important to consider interoperability right from the start and ensure that they can be deployed by even non-specialists in real factories. So that's the key takeaway that I want to leave with. I'll pass it on to Jillian.
Hi, sure. Yeah. it looks like we're coming up to the next hour, so maybe we have time for just one question. But please do, if you have a question, do drop it into the chat box and we will try to respond after the webinar. But one question that I think would be good to get to is what is the percentage of smart manufacturing using AI in the industry as of today? So what is, and what do we forecast that to be? And what is the share of it, if we can break that down for large, medium, and small enterprises in smart manufacturing?
I can take that up. Okay, yeah, we've seen many surveys and statistics being floated, but in our view, the propensity for an enterprise to adopt smart systems depends on what type of a digitizer or digitalization journey that they are on, right? So if they are an enterprise digitizer and who have looked at the sensorization and data management and safety rules that have already been in place for a while, it's much more easier to think about adopting smart systems that can perform certain tasks. And there is a statistic that we want to throw out here, like approximately about 35% of manufacturers globally have reported using AI in some form. And this is according to Entity Data and Manufacturing Leadership Council survey. And it gives you an indication that it's there, but it's not yet there in full scale. And we believe that this will only accelerate. The trend is being driven by competitive pressures and the need to improve efficiency and resilience, right? So there is the technology is available. The bottlenecks and barriers are essentially at the enterprise level, and it requires a complete reinvention of the full stack and to decide who your strategic partners are going to be. In terms of the enterprise size breakdown, there are companies at different sizes exploring adoption of AI. Among the US manufacturers, about 29% already use AI at the facility or the network scale, with another 23% running pilots. In contrast, if you think about small and medium-sized manufacturers, they report about 8% in use today, with another 12% in the process of implementing solutions. This is on the US side. On the European side, we see that across all industries in 2024, about 11% of the small enterprises and 21% of the medium and 41% of the large enterprises used AI. And there is, this gap between the size of the enterprises who are, more pro adopting AI in different forms. And in terms of the market growth and forecast, there are broad estimates on AI, anything AI in the market right today. So, we've looked at certain numbers and we see that, the AI and manufacturing market was valued at somewhere between $5 to $6 billion in 2024, and it's projected to reach little over $200 billion by 2034. And it's essentially to state that, okay, we have AI solutions, there are certain pilots in progress, but all depends on how much of that pilots get translated into production pipelines, right? So, and it's about how manufacturing companies are able to extract the value, and the value is going to be delivered in terms of manufacturing productivity, throughput, or OEE, and all of these matters, and how much of that recognized value can be provided as proof of value delivered by the solution providers. So all of this will translate to how fast we see the growth in AI adoption across the manufacturing, and it depends. We want to see high double-digit growth, but it all depends on how fast we can move from pilot to production, and the scale of migration also matters.
Great. Thank you. Thank you, Isaac. And yeah, no, that was wonderful. Thank you, Isaac. Thank you, Isaac, again for presenting, and for Kalyani as well. And on behalf of Everest Group, thank you all for joining us. We hope that you're leaving this session not only with a sense of the technologies, but also some strategic implications for your organizations. So until next time, we hope that you stay resilient. Thank you.
Thank you. Thank you, Julian.
Thank you.
Thanks, Kalyani. Thanks, everyone.